Chapter 9, Stoichiometry and the Mole. This is one of my favorite parts of chemistry. It's neat to try and see how balanced you can make an equation. Whatever goes into an equation must come out of the other side of the equation. I'm a very black and white kind of person, and to me this is something that's very tangible, and we use our periodic tables to help solve a problem. So if you follow my lecture very carefully and use it as a tool to help you figure out your assignments and such, I think you're going to find that you really enjoy it too. So take your time, pause as needed to try and absorb the material as we go through it, as I'm going to ask you several times to pause, figure out the problem, and hit play to see if you got the answer right. So be prepared to do that as we move through this. So what is stoichiometry? This is the study of the quantitative aspects of chemistry. It applies to balanced equations only. It answers how much? The amount of reactant needed and the amount of product that is made. So consider that you're making a cheesecake. It's one of my favorite things. And it requires 5 eggs to prepare. Well, how many eggs would be needed to make 2 cheesecakes? Well, this is relatively simple, right? You say, well, duh, Becky, I need, 10 eggs. Well, we do need to use conversion factors because not all of our stoichiometry is going to be as simple as saying, well, duh, 2 cheesecakes, 5 eggs piece equals 10 eggs. Conversion factors are as such. If we make 2 cakes that require 5 eggs per cake, we get 10 eggs. What I really want you to notice is that the cakes are opposite each other, so it cancels out. What we're then left with is eggs. This is called unit analysis. We find the conversion between the units, for example, 5 eggs for 1 cake. We use this to find our final answer. So if 1 cheesecake requires 1 cup of sugar and you have 3 cups of sugar, how many cheesecakes can you make? Well, here we have 3 cups of sugar times 1 cake needing 1 cup of sugar. The sugar cancels out and we're left with 3 cakes. So next we're going to look at the mole. What is a mole? You may or may not have heard of a mole when it, in regards to how much of something, but it relates to the number of atoms or molecules to grams. Individual atoms cannot be counted because they're extremely small. It is a set number of atoms or molecules. It's similar to something like there's 12 eggs in a dozen. There would be 6.02 times 10 to the 23rd, which is what this number is, eggs in a mole. So imagine yourself taking 6.02 times 10 to the 23rd, or this number you see in front of you, eggs, and adding it to a bin. That is a lot of eggs. Here we've got 2 trillion. It's bigger than that. So it's almost it's so hard to wrap your head around it, right? It is a huge number. This is known as Avogadro's number. He came up with this number. It's the number of atoms in 1 mole. So if you were to take, let's pretend an atom is like the egg that I just mentioned, each atom, and put it in a pile, it would take 6.02 times 10 to the 23rd of those items, which is that really big number I just showed you, put on a pile. Now you can imagine a mole of atoms is going to be a lot smaller than a mole of donuts or eggs, right? So 1 mole equals 6.02 times 10 to the 23rd of something. Okay? So what is the approximate size of this? Well, a grain of sand is 1 mole. A mole of water is about 1 swallow. And a mole of sugar would fill your cupped hands. So let's consider this following chemical equation. This equation does not relate grams of compounds, but instead the number of molecules of each compound. So what this reaction is stating is that 1 molecule of H2 reacts with 1 molecule of I2 to form 2 molecules of HI. You can see that we have 2 hydrogens, and here are 2 hydrogens. We've got 2 iodine, which when you put the big 2 in front of it means there's 2 H's and 2 I's. Since a mole is simply a number of items, both are correct. We can assume that 1 H2 molecule and 1 I2 molecule react to give 2 HI molecules. And 1 mole of H2 molecules and 1 mole of I2 molecules react to give 2 moles of HI molecules. Same thing. So what is this relationship to grams? We can't count out individual atoms, so we determine the mass of them. This is where the periodic table is going to become like your best friend, okay? So molar mass allows the conversion between mass and moles and also between moles and mass. We simply replace the units of AMU, atomic mass unit, with grams to find the mass of 1 mole. Here's what this means. There's 3 examples down here. But let's say you had a pile of carbon. Carbon's easy to visualize. Think of it like coal, right? Black coal. So if you were to take an 6.02 times 10 to the 23rd carbon atoms and pick them up one by one and put them on a scale and weigh them, you'd have a little pile of coal, okay? They would weigh 12 grams on a scale, okay? So 6.02 times 10 to the 23rd atoms of carbon weighs 12.011 grams. If you look at the periodic table that you guys should all definitely have printed by now, you will see that number underneath the symbol. So every time I ask you for the atomic mass unit, sometimes the gram molecular weight I'll refer it to, especially in clinical chemistry, this is the number I'm talking about. That's how much 1 mole of carbon weighs. This is how much 1 mole of uranium weighs. Obviously, you can see it's a lot heavier. And 1 mole of hydrogen is very, very light, right? That pretty much floats in the air. So suppose you obtain 393.934 grams of gold. That's AU on your periodic table. What is the molar mass? How many moles of gold do you have? And how many atoms of gold do you have? So I've given you the tools to try and figure this out. Please pause the lecture at this point and try and figure this out without looking ahead to the answer, because I know a lot of you guys have the PowerPoint already. So here's our answer. The molar mass of gold, by looking at your periodic table, it's AU, is 196.967 grams per mole. You have 2 moles of gold here, okay? You know this because if you have 393 divided by 1.96, we would get 2 moles. And how many atoms do you have? Well, if you took 2 times 6.02 because you've got 2 moles, you would have 1.204 times 10 to the 23rd atoms. So looking at the molar mass of these molecules, add each piece of the molecule together. Let's consider carbon dioxide, or CO2. This is what this says. The molecular message says that for CO2, 1 carbon atom per CO2 molecule, right? There's 1, we can see it right here. And we've got 2 atoms per CO2 molecule. You can see the 2 right here. There's 2 oxygens. The little subscript means there's 2. The mole message says 1 mole of carbon atoms per mole of CO2 molecules, because there's 1 carbon. And we've got 2 moles of oxygen atoms per CO2, because there's 2 right here. So it means the same thing. So let's look at the molar mass of this whole shebang. Summing the molar mass. So here's what we do. We know in CO2 we've got 1 mole of carbon atoms, 12.011 grams per mole. We've got that. We know that up here because I taught you that earlier, right? If you look at oxygen on your periodic table, 1 mole is 15.999. And if you look at another mole of oxygen, it's the same as the first mole, right? Because we got 2 of them. It's another 15.999. 1 mole of carbon dioxide molecules weighs 44.009 grams. So let's convert this with molar mass. The mass of 1 mole of water is 18 grams per mole. Here we can see that 18 grams of water over 1 mole of water, and 1 mole of water over 18 grams of water. So those are the conversion factors that you would use. So how many moles of water are in 250 grams of water? Pause the lecture here and see if you can figure out the conversion factor. Remember, 1 mole of water weighs 18 grams. Using the conversion factor that you just saw, 250 grams of water times 1 mole of water over 18 grams of water equals 13.88 moles of water. Your conversion factor is 1 mole of water is 18 grams. So how many grams of water are in 13.88 moles of water? Pause here, see what you get, and hit play to find the answer. So here we've got 13.88 moles of water times 18 grams of water per mole of water. Always remember, what you're trying to cancel out has to be opposite each other. And we get 250 grams of water. So when we're looking at stoichiometry conversions, there's no direct path to go from mass to atoms, okay? You have to go from mass times mass over molar mass to get moles, or from moles to moles times molar mass to give you mass. So there's always going to be a couple steps present, which is why we need to use the conversion factors. So bear with me for a minute here. We're going to look at the theoretical yield. This is the maximum amount of product that can be produced from a certain reactant amount. If the reaction says that you've got 2 moles of hydrogen and 1 mole of I2, they'll react to give 2 moles of HI. But 1 mole of H2 has a mass of 2.0152, get that from the periodic table, and 1 mole of I2 has a mass of 253, and 1 mole of HI has a mass of 127.913. So what this is saying is 2.015 grams of H2 and 253.8 grams of I2 react to give 255.826 grams of HI. That's our theoretical yield. That's what we're going to assume that we get by adding those together, right? The actual yield is the amount actually produced in the chemical reaction. Usually it's less than the theoretical yield because of side reactions and side products, but conservation of mass would still be observed. So then that gives us our percent yield. We're going to do this in lab this week, or if you're watching this after the lab, you've already done this. So hopefully this will either get you ready for the lab, or after you do your lab, it'll kind of all come to be like, oh, okay, that makes more sense now. Our percent yield is the actual divided by the theoretical times 100. So what would be the percent yield if 225.1 grams of HI were isolated out to a possible yield of 255.824 grams of HI? We would take the actual yield divided by the theoretical. Our percent comes out to 87.99%. Our molecular formulas can also yield conversion factors. So 2 moles of hydrogen atoms per mole of H2 molecules from the formula H2, 2 moles of iodine atoms from 1 mole of I2 molecules form formula I2, 1 mole of hydrogen atoms to 1 mole of HI molecules from the formula HI, and 1 mole of iodine atoms per 1 mole of HI molecules form the formula HI. Let's consider this equation. 4 aluminum plus 3 oxygen give you 2 Al2O3. What is the conversion factor between aluminum and oxygen? And what is the conversion factor between O2 molecules and oxygen atoms? Pause here, use what you've just learned to see if you can come up with the correct answer, and hit play when you're ready to see the answer. Here are the conversion factors. We have 4 moles of aluminum per 3 moles of O2, or 3 moles of O2 per 4 moles of aluminum. They both mean the same. What is the conversion factor between O2 and oxygen? 1 mole of O2 per 2 moles of oxygen, or 2 atoms of oxygen over 1 mole of O2. So what would the mass of H2 be required to make 10 grams of HI? So grams of HI to moles of HI to moles of H2 to grams of H2. Here's the conversion factors that you would use. So if you need 10 grams of HI, we know that 1 mole of HI is 127.913 grams. Okay? In this case, our HI, grams of HI, cancel out. Okay? We then know there's 1 mole of H2 per 2 moles of HI. In this case, moles of HI are going to cancel out. We then know that 2.0158 grams of H2 per 1 mole of H2. And that's what we wanted to find. You need to end with a surviving unit, which is the mass of I2 or H2, and we got grams of H2 in the end. This moles canceled out. So we're left with 0.0788 grams of H2. Here's a quick steps to figure out stoichiometry. So this is a one slide shot for you for when you want to go back and figure this out. It's a nice resource. So here's another one. How many oxygen atoms are in 10.7 grams of oxygen, which is O2? Pause here. When you're ready to see the answer, continue on. From here, we got grams of oxygen to moles of oxygen to atoms of oxygen. So we start with our 10.7 grams of oxygen. We know there's 1 mole of O2 that weighs 31.998 grams. There's 2 moles of oxygen, 2 moles of oxygen atoms per 1 mole of O2, times 6.022 times 10 to the 23rd atoms per mole. This leaves us with 4.03 times 10 to the 23rd oxygen atoms. When in doubt, convert to moles. Next, we're going to talk about limiting and excess reactants. The limiting reactant is the reactant that's in short supply. This limits the amount of product that can be made. It will be completely used up. Excess reactant is just as it sounds. It's present in excess in the reaction. It's going to be left over. In a stoichiometry type reaction, it's the exact amount needed for each reactant present. And you can use any reactant in calculating the theoretical yield. In the limiting type reaction, a limiting reactant is present, but you must use the limiting reactant to calculate the theoretical yield. I have examples coming up. So here's how we find the limiting reactant. We write out the balanced equation. We calculate the number of moles of each reactant present, divide the moles by the coefficient in the balanced equation. The smallest mole to coefficient ratio is the limiting reactant. So here's the example. If you react 6 moles of propane with 29 moles of oxygen, what would the limiting reagent be? So here's our equation. C3H8 plus 5O2. So here's our propane, here's our oxygen. This gives us 3 carbon dioxide and 4 waters. We have 6 moles of C3H8 and 5O2, because we know that from up here. So 6 moles over 1 equals 6. 29 moles of O2 over 5 is 5.8. The smaller mole to coefficient ratio, meaning oxygen is the limiting reactant. And we got these from the coefficient on top. Now granted, in front of this C3H8 there's no 1, it's pretend. There's 1 there, okay? In O2 we've got a 5 up here, okay? Next, we'll look at combustion analysis. Think of like your engine in your car. We're burning a material to find its molecular formula. It combines each component with oxygen. Each oxide is massed to find the original composition. So in this case, there's a stream of oxygen that's being heated up, which turns into H2O and CO2 plus oxygen. There's an absorbent for water, an absorbent for CO2, and oxygen is pushed out the end. Let's consider a material that is found to contain 60% carbon, 4.48% hydrogen, and 35.5% oxygen. How do we find the elemental composition of this? Well, what we do is find the formula from the percent. Assume you have 100 grams of material. Convert the masses of each element to moles. You find the ratio between components, and if the ratio is not a whole number, adjust as needed to obtain those whole number subscripts. All right, so here, If a material, which we just mentioned, was 60% carbon, 4.48% hydrogen, and 35.5% oxygen, we know that a 100-gram sample, okay, would be 60 grams carbon, 4.48 grams hydrogen, and 35.5 grams of oxygen. Now we need to figure out the moles of each one. This is where your periodic table comes in handy. So we know we've got 60 grams. I taught you earlier that 1 mole has 12 grams. So we're left with 5 moles of carbon. 4.48 grams of hydrogen times 1 mole is 1.0079 per your periodic table is 4.44. And 35.5 grams of oxygen, and there's 1 mole of oxygen for 15.999, gives us 2.22 moles of oxygen. Okay. Now we divide by the smallest number of moles. The smallest number is 2.22. Okay. So here, multiply by 4 to obtain the whole number subscripts. We end up with 2.225 times 4, H2 times 4, and O1 times 4. Multiply through by a factor of 4 and we get C9H8O4. To determine that formula, here's a quick list of steps that we just ran through. Like I said, sometimes these slides are a nice guide for you as you're trying to do a few of these on your own. Next, we're going to look at empirical versus molecular formulas. Well, empirical formulas are the simplest one. It gives the most reduced ratio. So if we had CH2O, okay, that's pretty simple. The molecular formula is the actual molar ratio of elements in a compound. For example, C6H12O6 or C2H4O2, okay? To convert an empirical formula to a molecular formula, first we divide the molar mass of the compound by the molar mass of the empirical formula. So the molar mass of glucose is 180.155 grams per mole, and the molar mass of the empirical formula is 30.026 grams per mole. We multiply all of the subscripts in that empirical formula by the number calculated in step 1, which is what we did earlier. So how do we convert a molecular formula to a percent composition? First, we find the mass of each element in 1 mole. Divide the mass of each element by its molar mass and multiply by 100. That gives us the percent composition for each element. So let's find the elemental mass percentages for a compound with the formula C6H12O6. First, we find the mass of each element in 1 mole. Okay, so 6 moles of carbon times 12 over 1 is 72. 12 moles of hydrogen times 1.0079 grams per mole, etc. So you guys know where I got these numbers from. Okay, I didn't just make them up. That's why your periodic table is a fantastic tool for this stuff. So here are the grams of each of our elements within that formula. So now we're going to find the elemental mass percentages for a compound with the formula C6H12O6. We're going to divide the mass of each element by molar mass and multiply by 100. Okay, so we knew there's 72.066 grams of carbon divided by 180.155 times 100 is 40%. 6.71% hydrogen and 53.28% oxygen gives us about 100%.